So our goal today is I can use calculus to optimize different situations and scenarios. The main thing that I want us to remember today, when we talked about optimization at first, okay, here we go. All right, to optimize means to make the best or most efficient use of a situation or resource. So that can either maybe mean maximizing, like I might want to maximize the space that I have or maximize the time that I'm spending on something. Or it might mean, if I want to optimize, it might mean minimizing. Like I might want to minimize how much I spend when I go to the grocery store, okay? And so those are two different options, either maximizing or minimizing. And we can use calculus to help us do this. We looked at the example of this polynomial function. And our maximums, our minimums, happened at these hills and valleys, okay, the tops of our hills and the bottoms of our valleys. And we know, based on everything that we've learned about derivatives so far this year, that at these specific points, our maximums and our minimums, our derivative is equal to 0. So that is the underlying calculus foundation that we're going to use for our lesson today, is when we take the derivative, we set it equal to 0, and it helps us find these maximum and minimum points. Okay? So we've practiced setting up these optimization problems. Like I said, today we're going to go the extra step and actually solve them. So let's take a look at example number 1. We want to find two positive numbers that satisfy the given requirements. The sum is 32 and the product is a maximum. So first step is to draw a picture. Here I don't really have anything that I can draw. Okay? So we'll go ahead and skip part 1 for now. Number 2 is we're going to write an equation that will be optimized. Okay? So I kind of have two different pieces of information here. So what is one equation that I could write using some of this information that I've been given? Yeah?
X plus y equals 32.
Yeah, my sum means addition. So x plus y I know is equal to 32. Okay? Yeah, and then I want to maximize my product. So product means to multiply. So then I have x times y equals my maximum. Okay, cool. So we've done step number 2. I've set everything up. I have my equation. This is what I'm trying to maximize or optimize. Oh, hi. You scared me. Okay. Let's see. A 1 and a new. Okay. This is for you new. All right. Okay, now, if I would take the derivative of this guy, at this point, I would have to use my product rule, and since I have a mixture of two variables, I would have to use my implicit differentiation. We're not trying to do that. We've done enough implicit differentiation with our related rates and stuff like that, so let's just make our lives a little bit easier and rewrite this equation in terms of one variable. Now, it doesn't matter if you want to rewrite it in terms of x or in terms of y. Either way is going to be okay and give you the same answer. Which one do you guys want to do? Rewrite it in terms of y? Okay, so to change this equation, luckily I have this other piece of information that's going to help me change all of my y's to x's. I subtract x from both sides. That gives me y equals 32 minus x. Okay. Now when I come over to my equation that I want to maximize, I'm going to replace or substitute my y with 32 minus x, and that will equal my maximum. And then I can go ahead and distribute as well. That way I still don't need to use the product rule. If I distribute, then I can just end up using my power rule. 32x minus x squared equals my max. So up to this point, we've done all of these steps. Okay? Now, I still haven't answered the question of find the two positive numbers. So this last step here, which is optimized by finding the maximums and minimums, you take the derivative and set equal to 0. That's what we're doing today. Okay? So here's my function. This is what I'm trying to maximize. If I want to find that maximum point, I can take my derivative and set my derivative equal to 0. Okay? Because when I do that, when I take my derivative and set it equal to 0, it will give me these special maximum and minimum points. Okay? So let's go ahead and do that. The derivative of 32x is 32 I'm going to write derivative here so that we know what's going on. Okay, and then the derivative of negative x squared, negative 2x. And I know that the derivative at any of maximum or minimum is equal to 0. Okay? Calculus is done. Now we are officially in the territory of Math 7. Okay? What do I do to solve for x? Okay? Yep, I need to subtract 32 from both sides. Okay? That will leave me with negative 2x equals negative 32. Then I divide by negative 2. So my x is equal to positive 16. Have I answered my question? No. What do I still need to find? Yeah, I'm halfway there. I want to find 2 positive numbers. So I found 1 positive number. Okay. So at this point, what equation, how am I going to find my y? What do you guys think? Yeah, let me just substitute it into x plus y equals 32. Okay, so now I need to find my y. Nice algebra 1 going on right here. Okay, x I know is 16. I can subtract 16 from both sides, and my y will also be 16. Okay. There we go. So if I want 2 numbers that add up to 32 and I want the biggest possible product, I'm going to want to use 16 and 16. Okay. I'm so glad I figured that out. I was just really walking around really wanting to know the answer to this question. Okay. Questions on this process? Okay. Let's look at example number 2. A rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular corrals. Good, okay. Corral. What does adjacent mean? Yeah, just right next to each other, okay? So I'm going to have 2 corrals right next to each other. What dimension should be used so that the enclosed area will be a maximum? All right. This is a perfect example of when I don't want to skip question number 1, or step number 1, draw a picture. Okay. So I have 200 feet of fencing, and I want to enclose 2 adjacent rectangular corrals. So here is my overall rectangle. Okay. And I want to split this up into 2 pens. Okay. I'm going to split it right down the middle. All right. I have 200 feet of fencing. What's that? The perimeter, okay? Now, I need to pay attention. In this case, my perimeter is not just this outside. I don't need to use the fencing just for the outside, but I also have that little line down the middle that I need to incorporate into my 200 feet of fencing, right? Now, I don't know how long all of these sides are going to be, so we can label them with variables. Doesn't really matter, okay? I know all of these are the same, okay? X, 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 okay? And I can use like Y for my vertical lengths. All of those vertical lengths are the same, and all of those horizontal lengths are the same. Okay, so my perimeter, if I wanted to write an equation that describes my perimeter, what would that equation be? Yeah, I have 4 x's and 3 y's, and all of that together makes up my 200 feet of fencing that I have. Okay. Now this is just like what I'm given. I'm not trying to maximize my perimeter because I only have 200 feet of fencing. What am I trying to maximize? My area. So what's an equation for the area, the total area of this guy? Yeah, my length times my width. Okay. This is what I'm trying to maximize. What's my length of this rectangle? 2x, right? I have x and x, so my length is 2x, and what is my width? Y. Okay. So 2x times y. So if I take this times this, that's going to give me my total area, which I want to maximize. Okay. Drawing a picture, very important, very helpful here. Okay. Okay, so I'm trying to maximize this guy. If I took my derivative right now, I would have to use product rule and implicit differentiation. So let's go ahead and isolate one of my variables so that I don't have to deal with that mess. Let's try isolating y this time. Okay? Or sorry, isolating x this time. Okay? It'll give us the same thing. It doesn't matter. So to get x by itself, I'll do minus 3y on both sides. That gives me 4x equals negative 3y plus 200. And then I need to divide everything by 4. X equals, we're not freaking out that we have a fraction. 200 divided by 4, 50. Okay. Now that I've isolated my x, I'm going to go back to my area function, okay, and replace my x with negative 3/4 y plus 50 times y. Okay. So let's simplify this a little bit. That will be, let me distribute this 2 through 2 times negative 3/4 will give me negative 3/2 y plus 100, and all of that is times y. Now I'm going to distribute this y through to make my derivative easier. Okay. So that will give me negative 3/2 y squared plus 100 y. Okay. $200 divided by 4 is 50, right? Yeah, okay. Just making sure. All right. So at this point, I've set up my entire equation. I've rewritten it in terms of one variable. Now I am ready to take my derivative. Derivative of a maximum is always 0. Okay. What is the derivative of negative 3/2 y squared? Yep, I'm going to take this to multiply it. Okay, so negative 3/2 times 2 will give me negative 3y. Now, because I don't have any x's in here, no need to do dy dx. I'm not even looking at x. Okay, so we're just treating y like any other normal variable. Okay. Plus derivative of 100y is 100. Calculus is done. Now we are in Math 7 again. If I want to solve for y, I need to subtract 100 from both sides. Okay. That will give me negative 100 equals negative 3y. Last, divide by negative 3. So my y is 100 divided by 3, which is approximately 33.33. And what would my units be on this, you guys? Yeah, feet. Okay. On these optimization problems, if we're working in a context, I want to make sure that you guys are including your units. I'm trying to find my dimensions, right? So I'm finding my length right now, or my width, whatever one. Okay, so I'm going to want to include my feet. Okay. All right, I found my y. So I know that for my corrals, each of these vertical lengths needs to be about 33 feet. And now all I need to do is go back and find what my x should be. Okay. I'm going to go and use my perimeter function since I know that's a set value that I have. Okay. So now I'm going to find x. So 4x plus 3. What? Oh, yep, I could use this one. I could definitely use this one. My inclination, I always like to go back to the original equation in case, well, I guess if I made some mistake here, anyway, yeah. This is, never mind. This works great. 4/3 y plus 50. And when I substitute in, I'm going to substitute in my fractional answer to just try to be as precise as possible, and then I'll round at the end if needed. So 3/4 y times 100 thirds plus 50, okay? This will cancel, so that will give me negative 25 plus 50, which equals 25 feet, okay? So if you want to plug into your original perimeter equation or this equation, which we already have isolated for x, both work. Now these answers make sense, right? Like if I would have gotten a negative dimension, I would think to myself, okay, that's not possible for me to have a negative length, so I need to go back and check my work. Okay. Okay. Let me draw an arrow so that we know we came here. Any questions on this guy? All right. Example number 3, a production facility makes face masks. The total cost for producing X face masks in a day is given by this function here, okay? How many face masks per day should they produce in order to minimize production costs? Okay. Any ideas what I want to do here? I'm trying to figure out how many face masks so that I can minimize production costs. How could I find a minimum? Yeah, minimum mean, wait, what did you say? I didn't hear you.
Lower money.
Lower money. Yeah, so I want to spend the least amount of money as possible making these face masks. Okay. How could I figure out how to do that though? Trying to minimize my production costs. Yeah. If I want to find those points that are the minimums, all I need to do is take the derivative and set that guy equal to 0. So here's my function, c. I want to find c prime, so let's go step by step. Derivative of 25,000, or 22.
50,000.
I'm so bad at saying numbers. I mess it up all the time, and my husband's like, you are literally a math teacher. And I'm like, big numbers are hard to say. 250,000. 0. Okay, good. The derivative of 0.08x is 0.08. Okay. Oh, what about this? Yeah, I can either use my quotient rule, or since I don't have a variable on top, I could rewrite this guy as 200 million x to the negative 1. So then that would give me a derivative of negative 200 million x to the negative 2. Okay. So there is my derivative. And if I want to find my minimum, then I need to set this derivative all equal to 0. Okay? Now I'm going to rewrite this x to the negative 2 as a fraction. Okay. All right, now this is going to be a little more complicated to solve. We're moving into some algebra 2 territory here. Okay, that's okay, we can handle it. What would be the first thing I want to do to find what x is equal to? Yeah, whenever you have any extra numbers floating around that aren't attached to your variable, good rule of thumb is just get rid of that guy first. Okay, so let's subtract 0.08 from both sides. That gives me negative 0.08 equals negative 200 million divided by x squared. What could I do now? Yeah, I hate it, like, makes things a little more complicated when my variable's in the denominator of my fraction and I'm trying to solve. So an easy fix to that is just multiply both sides by your denominator. And that will cancel your variable out from your denominator and will give you negative 0.08x squared equals negative 200 million. Okay. And now this is great. Now we're back in some algebra 1 territory. We're really just reviewing our problem solving, equation solving skills. I don't know what this is. You can use a calculator. I'll give you guys a calculator on the test. You can use a calculator on your homework. 1, 2, 3, 1, 2, 3 divided by negative 0.08. Okay, gross. So what I'm going to do is I'm just going to take the square root right now. I'm going to get rid of my negatives. Okay, so the square root of, oops. Square root, okay. 1, 2, 1, 2, 3, 1, 2, 3 divided by 0.08. Cool. 50,000. Okay. So if this production facility wants to have the lowest possible production costs, they would want to make 50,000 masks a day. Okay. Now you might think that if you're running a factory or a business that, oh, well, if I want to make the most money, I should just make the most masks possible in a day. But you need to think about like maintenance costs for the machines, labor costs for the workers. Like once you start getting into overtime, you're actually not going to be making as much money because you have to pay people more. Anyway, so that's where it might not make sense to make just the most possible mass. We want to find what's going to lower our production costs. Okay, and my units on this X should be, yeah, masks. Yep. So I want to make 50,000 masks per day. Cool. All right. Example number 4, find the point on the graph of the function y equals x squared that is closest to the point 2, 1/2. Okay? All right. These are our favorite ones. Here's my parabola. Okay. Y equals x squared. Normally I can make it go pretty. There we go. Okay. And here's my point 2 and 1/2. So I'm trying to find which point along my parabola. So if I'm trying to minimize the distance, that's our beautiful distance formula, okay? Which is just the Pythagorean theorem, okay? X minus x1 squared plus y minus y1 squared, the square root of that, okay? D stands for my distance. Now, I already have some x's and some y's that I can substitute in, okay? Because I know one point has an x of 2, and my other point, or that point has a y of 1/2. Okay. So I'm almost ready to take my derivative here. The last thing I want to do is just rewrite my y in terms of x, because I have a mixture of x's and y's right now, so I don't want to have to use implicit differentiation. So y is equal to what, you guys?
X squared.
Yeah, x squared. So I'm just, instead of writing y, I'm going to replace with 1/2. Now I'm going to have to, we'll clean this up a little bit. Plus, okay, x squared minus 1/2 squared. All right. So now, and I want this distance to be my minimum. I want them to be as close together as possible. Any ideas on what I could do to clean this up before I take my derivative?
Change the square root into...
Okay, great. So I can change my square root into all of this to the 1/2 power. Okay. Perfect. Anything else I could do to clean this up a little bit? I think if I distribute this guy, if I expand, then I'm not going to have to use my product rule or my chain rule again. Okay. So let's go ahead and do that. If I multiply x minus 2 times x minus 2, what will that expand out into? X minus 2 and x minus 2. That will turn to x squared minus 4x plus 4. Okay. Let's go ahead and expand this guy out too. All right. Plus, when I expand this out, oh, I didn't, let me. Okay. X squared minus 1/2 squared would turn into x squared times x squared is x to the 4th. Okay. Negative 1/2 x squared, and I'll have another negative 1/2 x squared turns into negative x squared plus 1/4. Okay. I'm just going a little bit quicker through that multiplication, but you guys, take your time doing that if you need to. Now I can combine some like terms, so I'm just kind of cleaning up the inside of my chain rule a little bit. X squared, and I have a minus x squared, so those things will cancel. I have x to the 4th right here. And then I have minus 4x. And then if I have 4 plus 1/4, that will turn into 17/4. Okay. This looks a lot easier to differentiate than this. Okay? So we are just using our algebra skills to make our calculus life a little bit easier. Now we are ready to take the derivative. All right, derivative of a minimum is always 0. Okay. What's this derivative going to be? Yeah, I'm going to use my chain rule. So what's my outside? Something to the 1/2 power, and my inside is x to the 4th minus 4x plus 17/4. So chain rule tells me take the derivative of your outside. So that would be what? Derivative of something to the 1/2 power. 1/2. What's my inside going to be? Yep, keep the same inside. Chain rule is derivative of your outside. Keep your inside the same. Then I subtract 1 off my exponent, which gives me negative 1/2. Multiply by the derivative of my inside, which is what? 4x cubed. 4x cubed minus 4. Okay. This looks really complicated because we now have to solve for x. Okay. It's not that bad though. I'll show you guys if I rewrite this guy. Okay. At this point, you could actually just type this entire thing into your calculator, like your 0 equals blah, 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 and that will give you your answer. But I want to show you guys that this isn't as bad as it looks. I'm going to rewrite this negative 1/2. I'm going to put him back in my denominator, okay, as a square root. X to the 4th minus 4x plus 17/4. And then my numerator is going to be this guy right here. Okay. So I just had, now we're in pre-calculus solving. Okay. I have a rational function. Okay. If I want to know when a rational function is equal to 0, what do I need to do? I want to know when this guy is equal to 0. Think, I just have a fraction right here. When is a fraction equal to 0? When your numerator is equal to 0. Okay? So this whole thing, like think about it. If I have 0, let's simplify this a little bit, is equal to x over 4. Okay? X has to be 0, right? So we just need to look at when my numerator is equal to 0, okay? So we can essentially ignore this whole denominator. So that's why it doesn't end up being as bad as we think it's going to be, okay? And then I add 4 plus 4. Okay? 4 equals 4x to the third divided by 4. 1 equals x to the third, so x equals 1, okay? I don't have any units here. So you can either like rearrange, think about your pre-calc skills, or I want to show you. Desmos is the best thing, okay? If you just type this whole equation, 0 equals 1/2, and you can do this on your graphing calculator as well. X to the fourth minus 4x, oh no. X to the fourth minus 4x plus 17 fourths to the negative 1/2. Oh my gosh. Okay. To the negative 1/2. Okay. All multiplied by 4x to the third minus 4. Okay, there. So I type this whole thing in, and then wherever your vertical line appears, that's going to be your solution. Okay? So in this case, 1, which is great. That's what we found. And then my last step I need to do is just find my y, right? I have my x, but I want to find my y. Going to use this. Find y. Okay. Y equals x squared. If x is 1, then y is also 1. So this point is going to be what is closest to 2 and 1/2. So one thing I want you guys to think about as you're solving these is that we're using our problem solving skills, right? Our calculus ended right here. Really the only calculus we did was just we took the derivative, but there's a lot of setup and a lot of simplifying that that happens after we take the derivative and before, okay? And that's all your algebra pre-calculus skills that you guys have learned before. All right. How are we feeling? Okay. We're so what? We're confused? We okay? Okay. It's just, think about like the problem solving packet that you guys did, okay? Just look at each individual situation, okay? Think, I have all the tools I need to figure this out. It's 1,000 degrees in here. You're cold?
I'm okay. I
I'm
don't really feel anything. I'm wearing 2 jackets right now.
I'm hot.
like sweating, but our hot flash for the last period.
Yeah, wow. Okay. Last example. Alright, you guys are gonna kind of, well, I don't want to put a bad taste in your mouth, but I already did. Okay. The most important part is setting this guy up, okay? This is our problem solving skills. So here we go. We have 2 towers that are 30 feet apart. One is 12 feet high, the other is 28 feet high. There's a stake in the ground between the towers. The top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? So these, maybe like you guys don't care about this, obviously, maybe right now in your lives, you're like, I never need to figure this out. But these are the kind of things that like physics people and engineers are figuring out. I've never seen Mission Impossible, but I've started watching the Mission Impossible series. Have you guys seen Mission Impossible?
Yeah.
So this is like, I'm thinking of, I think it's the 3rd one, where like Tom Cruise he's like jumping from the top of the building in Dubai, and he like needs to make it to the other building, and he's like doing all this math to figure out like the angle and like how much wire he needs. Anyway, so that's what you guys are now prepared to be special agents, okay? Except he figures this out in like 2 seconds. But anyways, so let's draw a picture to help keep us organized. I have 2 towers. All right, I know one tower is 12 feet, and the other tower is 28 feet. And I also know that these towers are 30 feet apart. Okay. And I have a stake in the ground somewhere in between. I don't know where, so let's put it here. Doesn't really matter. Okay. And then there's wires going from the top to the bottom. Wow, what does it look like I have? Some triangles. Okay. Probably gonna maybe use Pythagorean theorem. Okay. Do I know what this length is right here? No. And do I know what, I don't know like where the stake is in comparison to the 2 different towers. So if I don't know something, what could I use? A variable. So let's say that this distance is x. Okay. I don't know how far it is from this 12-foot building. If this distance is x, what is this distance? 30 minus x, right? We could call it y, but then I'm just getting into a mess of, remember we're trying to just, as much as possible, stick with one variable, okay? 30 minus x, okay? What am I trying to minimize here? The wire. So this guy and this guy is my wire. I'm trying to minimize that. Well, what is this side and what is this side of my triangle? How could I figure that out? Pythagorean theorem, right? My Pythagorean theorem just tells me, okay, let me color code this for you guys. Okay, so here's my green triangle. So this green length is going to be equal to, let's just call it the green side right now. So the green squared is equal to what? What would my Pythagorean theorem tell me? X squared plus 12 squared. So my just green is going to be equal to the square root of x squared plus 12 squared. Okay. So this is my square root of x squared plus 12 squared. That's just using my Pythagorean theorem. Okay, so instead of calling this like hypotenuse or y or anything like that, I know I can describe this side using my x. So that's what we want to try to do. Okay. Now, let's do blue. Okay, my blue side, my Pythagorean theorem tells me hypotenuse squared, so blue squared is equal to what? My other side squared, 30 minus x squared plus 28 squared. And then if I want to find just blue, not blue squared, I'll take the square root of this. Okay. 30 minus x squared plus 28 squared. Okay. All right. And so what am I trying to minimize again? The wire, which is, yeah, green plus blue. Okay. I want to minimize that guy, so I want to minimize, we found out that green is square root of x squared plus 12 squared. I'm already sensing the excitement of when we're going to differentiate this. Oops, yeah, 30, oh, oops, hold on, this is 30 minus x squared. It's cold? You guys. So if I want to minimize this, I would take the derivative and set it equal to 0. I did it on my notes, but I'm not going to make you guys do it. It's too complicated. Happy Friday, you don't have to take the derivative of this. Okay? Alright, I feel like I need to show you the Mission Impossible scene. I think it's, okay, let's see, Mission Impossible. Tom Cruise jump. Oh yeah, here. Yeah. Yes. Happy birthday, by the way.